The universe drifts apart in silence. Galaxies, vast and ancient, slide away from one another across the abyss, like lanterns carried on a tide too slow for human eyes to witness. Their light, stretched into deeper shades of red, whispers of distance, of movement, of time unraveling. Beyond them, a darkness swells, not empty, but infinite, a canvas where every star is a fleeting spark against eternity. Threaded through this night is a faint murmur, a ghostly remnant of fire, the cosmic microwave background. It washes across the universe like an echo, older than any galaxy, older than any star. It is the faint afterglow of a time when the cosmos itself was newborn, its heat cooling, its first atoms forming. A frozen memory of beginnings, imprinted into the fabric of space. But here lies the tension: if everything is rushing apart, if all distances widen with every heartbeat of cosmic time, where did it begin? If the river of time is followed backward, its branching streams converge, narrowing, compressing, until they vanish into a single point, a drop of unimaginable density, where the laws of physics collapse into silence. Was there truly a first instant, a singular spark that tore existence from nothing? Or is the universe eternal, a stage without beginning, where creation and destruction endlessly repeat? The galaxies carry their secrets as they drift, the microwave whispers hum quietly in the background, and the night sky stares back with a haunting question: did the universe have a beginning, or has it always been here? Before the birth of modern science, the question of the universe's origin was not measured in equations or traced in the redshift of galaxies. It was woven into myth, whispered around fires, etched in stone, carried in the chants of priests and poets. Across cultures, across millennia, human beings looked upward and wondered, where did it all begin? Some believed it had no beginning at all. In India's ancient Vedic hymns, the cosmos is portrayed not as a single act of creation, but as a cycle, an eternal breathing of the universe itself. Worlds emerge, flourish, collapse, and then are born again, like waves on an endless ocean. Time is not linear but circular, stretching backward and forward with no first dawn. The Greeks, too, wrestled with the mystery. Hesiod's Theogony sang of primordial chaos giving birth to gods and worlds. Yet the philosopher Aristotle imagined something different, a cosmos without birth, without death. For him, the heavens were eternal, a perfect and unchanging sphere surrounding the earth. Stars did not ignite or fade. They circled endlessly, immune to time's decay. The universe, in his view, simply was, a steady, everlasting stage upon which the drama of life unfolded. This idea of eternity carried deep philosophical weight. To imagine a beginning was to imagine change, imperfection, instability. And for ancient thinkers, perfection lay in what was eternal, not what was temporary. The eternal cosmos was an idea of balance, harmony, and permanence. Centuries later, in medieval Europe, the notion of cosmic eternity clashed with theology. Christian doctrine, rooted in Genesis, spoke of a universe with a beginning, a divine act of creation. But many philosophers, influenced by Aristotle, argued otherwise. They claimed the universe stretched backward forever, with no single moment of birth. To them, eternity was not only natural, it was necessary. When the scientific revolution dawned, the eternal universe still lingered in the background. Galileo peered through his telescope and saw mountains on the moon, moons circling Jupiter, the rough imperfections of a sky once thought flawless. Yet even as the old model of perfect spheres crumbled, the larger assumption, that the universe itself was eternal, endured. Isaac Newton's laws of motion painted a cosmos like a grand machine. Infinite space, infinite time, filled with stars held in balance by gravity. The heavens might shift, comets might blaze, planets might move, but the grand stage itself remained eternal. Newton's God, for many, was not the creator of time's beginning, but the architect of its eternal order. This vision of an eternal, unchanging cosmos fit comfortably within scientific thought for centuries. It carried a sense of stability, a reassurance that the universe was not fragile, not fleeting. If time had no birth, then neither did it have an end. Existence stretched infinitely in both directions. But hidden beneath this reassurance was a resistance, quiet but profound. To suggest that time itself could have a beginning felt almost heretical, even to science. A beginning implied a cause, an origin, perhaps even an intention. For many scientists and philosophers, this strayed dangerously close to theology. It blurred the boundary between empirical study and metaphysical belief. If the universe had always been here, there was no need for a moment of creation, and no uncomfortable questions about what, or who, might have existed before. As astronomy advanced, this resistance continued. Even in the 19th and early 20th centuries, most scientists assumed a static, eternal cosmos. Stars were thought to shine forever. Nebulae were believed to be eternal clouds, drifting timelessly in space. Time stretched infinitely backward, a steady river with no source. And yet, hidden in the heavens, signs of change lingered. Stars did not live forever. They burned, they exhausted, they collapsed. Observations hinted at galaxies drifting, nebulae igniting, processes that suggested not eternity, but evolution. The universe seemed less like an unmoving stage and more like a story that might have begun somewhere. Still, for centuries, the idea of cosmic birth was suppressed by philosophy as much as science. The eternal cosmos was not only a scientific assumption, but a philosophical shield against the frightening possibility of a true beginning. A beginning demanded answers that no equation could yet provide. The eternal universe was not simply a theory. It was a comfort, a resistance, a refusal to stare into the abyss of nothingness. To claim that the universe began was to admit that time itself is fragile, that all of existence, galaxies and stars and atoms, might rest upon a singular moment, a moment when nothing became something. For the ancient world, and for centuries of thinkers that followed, such an idea was unthinkable. Time, they believed, had no birth. The cosmos, they said, had no first instant. Eternity was safer. Eternity was simpler. But eternity could not endure. Because in the 20th century, with the sharpening of telescopes and the quiet persistence of mathematics, the universe would reveal a deeper secret. A secret that shattered the comfort of eternity. A secret that whispered of a beginning.
In the early years of the 20th century, the universe was a mystery painted in starlight. Telescopes reached farther than ever before, but the cosmos seemed vast, silent, and unchanging. The night sky gave no hint of motion on its grandest scales. The stars circled in patterns written long before humanity's birth, and to the scientists of the time, the universe was eternal, infinite, and still. Into this vision stepped Albert Einstein. In 1915, he unveiled a theory that would bend the very foundations of physics, the general theory of relativity. It was not simply a new equation, it was a new way of seeing. Space and time were no longer fixed backdrops. They were flexible, woven together in a cosmic fabric, bending beneath the weight of matter and energy. Relativity revealed that the universe was not a rigid stage, but a living structure. Stars, galaxies, and even light itself moved not through space, but with space, carried along by its curvature, guided by its geometry. The cosmos was dynamic, a vast ocean that could ripple, bend, and shift under the pull of gravity. Yet hidden in the mathematics was a disturbing implication. If space and time were flexible, then the universe could not remain perfectly still. According to Einstein's own equations, the cosmos should either expand outward or collapse inward under the relentless grip of gravity. Stability was not natural. Change was inevitable. But Einstein resisted. The very idea that the universe might evolve was almost unthinkable in 1915. The prevailing wisdom, carried through centuries of philosophy and science, spoke of eternity and permanence. An expanding or contracting cosmos was not only unimaginable, it was unacceptable. So Einstein intervened in his own creation. He modified the equations of general relativity, adding a new term, the cosmological constant. With this mathematical adjustment, the restless universe was forced into balance. Gravity, which pulled matter inward, was countered by a gentle outward push, a static equilibrium that held the cosmos still. The cosmological constant was not born of evidence. It was born of necessity, a tool to preserve the vision of a stable, eternal universe. With it, Einstein tamed his equations, compelling them to reflect the world he and most others believed to be true, a cosmos infinite in age, unchanging in its grandeur. Yet, even as he wrote these equations, the tension remained. Deep in the structure of relativity was the whisper of something more profound, the possibility that the universe itself might not be eternal, that it might evolve, shift, and even originate from a beginning. Einstein himself wrestled with this tension. To abandon a static cosmos was to abandon centuries of thought, to suggest that time itself might have a birth. The implications reached beyond science, touching philosophy and even theology. For many, the idea of a beginning was a step too close to creation myths, too close to questions that physics was not ready to answer. And so Einstein clung to his static universe, convinced that nature would prefer stability over chaos. He believed he had captured reality in its purest form, balancing the cosmos upon the knife's edge of mathematics. But history would reveal an irony. The very theory he created, the equations of relativity themselves, contained the seeds of a universe far more dynamic than he imagined. Hidden in their logic was the truth that the cosmos could not remain still forever. Space itself was destined to move, to stretch, to carry galaxies outward in an ever-widening expanse. Others would see what Einstein chose not to. Mathematicians like Alexander Friedmann and Georges Lemaître took the equations at face value. They stripped away the cosmological constant and let relativity speak for itself. What it revealed was astonishing, a universe that was not static, but expanding. At first, Einstein dismissed these ideas as fanciful. He is said to have called Friedmann's work suspicious and doubted its validity. To Lemaître, he remarked that his physics was correct, but his interpretation was abominable. Yet both men had glimpsed the deeper truth buried in Einstein's mathematics, the first hints of a cosmic beginning. The irony is striking. Einstein had given humanity the tools to discover the Big Bang, yet his own resistance kept him from seeing it. His cosmological constant, once a lifeline to stability, became what he would later call his greatest blunder. And yet, this blunder was not meaningless. The cosmological constant would return decades later, not as a mistake, but as a clue, a hint toward the mysterious force we now call dark energy, the driver of the universe's accelerating expansion. Einstein, unknowingly, had touched a truth that even now science struggles to understand. But in 1915, none of this was visible. To Einstein and his contemporaries, the stars above remained calm, their positions steady, their patterns eternal. The universe was static because it had to be, because anything else was too radical to believe. The stage was set, though the actors had not yet moved. The mathematics of relativity had planted a seed, and in time, that seed would grow into one of the most profound revolutions in human understanding. The universe would not remain static. It could not remain eternal. For now, Einstein's cosmos stood frozen, a vast, eternal cathedral, upheld not by observation, but by a constant he invented to keep it still. But beyond the horizon of knowledge, the galaxies were already drifting. Space was already stretching. And the universe, silent but unstoppable, was preparing to reveal its motion. For centuries, the night sky was thought to be a grand stage, vast, eternal, and unchanging. The stars glittered like jewels fixed in a dome of silence. Galaxies, though not yet understood as such, were imagined as luminous clouds, drifting eternally in a static firmament. The cosmos appeared still, frozen, as though time itself moved only within the small theater of Earth. But in the quiet years of the early 20th century, a new kind of evidence began to whisper of motion on the largest of scales. The first signs came not from great telescopes or dramatic revelations, but from the patient persistence of a single astronomer. Vestos Slifer, working at the Lowell Observatory in Arizona, turned his spectrograph toward faint smudges of light, spiral nebulae, as they were then called. By dispersing their glow into rainbows of color, he measured their spectra with painstaking care. And in these patterns, he found something startling. The lines, which should have rested at familiar wavelengths, were shifted. Almost all of them leaned toward the red. This redshift was more than a curiosity. In physics, it meant that the objects were receding, their light stretched longer as they moved away. Slipher's measurements, beginning in 1912 and accumulating through the decade, revealed a silent truth. These nebulae were not still. They were rushing outward, away from Earth, at speeds of hundreds of kilometers per second. At first, his findings were puzzling, even ignored. The nature of these spiral nebulae was itself uncertain. Were they clouds within the Milky Way or vast systems of stars beyond it? Many astronomers hesitated to interpret what the redshifts truly meant. But Slipher had uncovered the first glimmers of a cosmic motion that would soon shake the very foundation of science. It was Edwin Hubble, working with the 100-inch Hooker telescope on Mount Wilson, who connected the pieces. By 1924, he had shown that these nebulae were not small, local clouds. They were entire galaxies, island universes unimaginably far beyond the Milky Way. Their distances, measured through Cepheid variable stars, placed them millions of light years away. And when their distances were compared with Slipher's redshifts, a profound relationship emerged. The farther a galaxy lay, the faster it seemed to be receding. This pattern was not random. It was law-like, precise, undeniable. The universe was not static at all, it was expanding. This revelation, announced in 1929, shattered centuries of assumption. The eternal, unchanging cosmos crumbled under the weight of observation. The night sky, once thought to be still, was alive with motion, galaxies rushing apart in every direction. The universe itself was stretching. Hubble's discovery became known as Hubble's law. Velocity increases with distance. Galaxies twice as far recede twice as fast. The cosmos was not fixed, it was dynamic, restless, unfolding. And hidden within this expansion was an even more haunting implication. If galaxies were moving apart today, then in the past, they must have been closer. If one rewinds the motion, step by step, epoch by epoch, the galaxies converge. The distances shrink, the space between collapses. Eventually, all must have been compressed into a single, unfathomably dense state. Here, for the first time, science confronted the possibility of a beginning. The thought was radical. It suggested that the universe was not eternal, not infinite in age, but finite, with a point of origin. Time itself could have a birth. Space itself could have once been compressed to nothing. The philosophical resistance was immense. Many clung to the vision of an eternal cosmos, unwilling to accept the notion of a beginning. Some scientists dismissed the idea outright, suggesting alternative explanations for the redshifts. Others sought comfort in the thought that perhaps galaxies drifted within a larger, eternal framework. But the data spoke clearly. The expansion was real, the pattern consistent. The cosmos was no longer a static cathedral. It was a river flowing outward, its currents carrying galaxies like leaves on a widening tide. The implications reached far beyond astronomy. If the universe had a beginning, then physics itself must confront the question of origins. What mechanism could ignite existence? What forces could hurl space and time outward from a singular seed? Was the beginning absolute, or merely a transition from something older, hidden beyond the horizon of knowledge? Hubble himself refrained from speculation. He presented the evidence, careful and restrained, leaving philosophy to others. Yet his discovery opened a door that could never again be closed. The universe was dynamic. It was expanding. And with expansion came the whisper of a profound and unsettling truth. The universe might not be eternal. The silence of the stars was broken by a new vision, a cosmos in motion, with a past, and perhaps even a moment of birth. The eternal night was no longer eternal. It was a story unfolding, and humanity had just glimpsed the opening chapter.
For most of human history, the heavens appeared eternal. The constellations turned above like clockwork, fixed and unchanging, a celestial dome without motion. To the astronomers of the 19th century, this vision of permanence still held sway. Stars twinkled. Nebulae shimmered faintly. But the universe itself seemed frozen, a grand stage that had always been, and would always be. Yet the first cracks in this vision emerged quietly, in the desert air of Arizona. At the Lowell Observatory, a patient astronomer named Vesto Melvin Slipher turned a spectrograph toward faint patches of light called spiral nebulae. Between 1912 and the early 1920s, he collected spectra of these ghostly smudges, spreading their light into lines of color, measuring their chemical fingerprints. What he found was unexpected. The lines were not where they should have been. They were shifted, nudged toward the red end of the spectrum. This redshift carried a simple but profound meaning: the nebulae were moving away. And they were not creeping at a gentle pace. Some fled at hundreds of kilometers per second, speeds unheard of in the celestial order. Slipher's results were puzzling. At the time, the very nature of these nebulae was uncertain. Were they clouds within the Milky Way? Or entire, island universes, beyond it? Whatever they were, the evidence whispered that they were not still. The heavens harbored motion far grander than anyone had dared imagine. It was Edwin Hubble, working with the 100-inch Hooker telescope on Mount Wilson in California, who brought the pieces together. By 1924, Hubble resolved individual stars within the spiral nebulae. Among them were Cepheid variables, stars that pulse with a predictable rhythm, their brightness tied to their true luminosity. By measuring these stars, Hubble could calculate distance. The results were staggering. These nebulae were not local clouds. They were galaxies, vast collections of stars, millions of light-years away. The Milky Way was not the universe. It was merely one galaxy among countless others. Then came the revelation that would change everything. Comparing distances with Slipher's redshifts, Hubble saw a clear pattern: the farther a galaxy, the faster it receded. This was not random drift. It was a law. A relationship now etched into science as Hubble's law. The universe was expanding. In that moment, the eternal cosmos shattered. The heavens were no longer a static stage. They were dynamic, restless, unfolding. Space itself was stretching, carrying galaxies outward on currents of geometry. The implications were dizzying. If the universe expands today, then in the past it must have been smaller. Wind the clock backward, and the galaxies draw closer, the distances shrink, the cosmos contracts. Extrapolated far enough, all of existence converges into a single, unimaginable density, a universe compressed to a point. Here, for the first time, science confronted the haunting possibility of a beginning. The thought was unsettling. A cosmos with an origin implied a moment when time itself ignited. What came before? What force lit the spark? The questions pressed against the boundary between science and philosophy, where mathematics collided with mystery. Resistance was inevitable. Many scientists recoiled from the idea of a universe with a beginning. The notion seemed too close to theology, too reminiscent of creation myths. Perhaps, they argued, the redshifts had another cause. Perhaps galaxies moved through space, not with it. Perhaps the expansion was only illusion. But the data held firm. Year after year, new observations confirmed the same truth. The galaxies were not static. They were receding, bound to a cosmic law of motion. The universe was not eternal in the way once imagined. It was a river, flowing outward from an unseen source, carrying time itself with it. Hubble, cautious by nature, did not leap to metaphysical conclusions. He reported what was observed: galaxies move away, velocity proportional to distance. Yet beneath the careful tone lay a silent revolution. Humanity now knew that the cosmos itself evolves. The stars above, once thought eternal, were part of a story with a past, and perhaps a beginning. The whisper of Slipher's spectra had grown into the proclamation of Hubble's law. The universe was expanding. And with that discovery came the first hint that all existence might trace back to a single moment of birth. The eternal night was no longer eternal. It had a history. And hidden within that history was a question that would haunt science for the century to come: if the cosmos is expanding outward, then what happens when one dares to follow it back, to the very first instant? In the early decades of the 20th century, when the fabric of the cosmos was just beginning to reveal its hidden motion, one man dared to ask the most unsettling question of all: if the universe is expanding, from what did it expand? That man was Georges Lemaître, a Belgian priest, mathematician, and physicist. He lived in the space between two worlds, the cloistered halls of faith and the rigorous frontiers of science. His black clerical robes hid not just the cloth of religion, but the fire of a mind that could read the mathematics of spacetime. Lemaître was not swayed by appearances. Where others clung to the eternal universe, he trusted the language of Einstein's equations. General relativity had shown that space and time were not rigid absolutes but a flexible fabric, one that could stretch, bend, and evolve. In those equations, Lemaître found a bold truth: an expanding universe was not just possible, it was inevitable. Working alone, he derived what the data of Vesto Slipher and Edwin Hubble were only beginning to whisper: galaxies flee one another not because of chance, but because the very stage on which they exist is swelling. He took the expansion to its logical conclusion. If the cosmos grows larger with time, then in the distant past it must have been smaller. And before it was vast, it must have been condensed into something unimaginably dense. Lemaître called it the primeval atom, a cosmic egg, the seed of everything, exploding into space and time. It was not a myth retold, but a mathematical consequence of relativity, carried to its deepest edge. In a single moment, the entire universe could be traced back to one origin, one primordial flash. But the idea was too radical for its time. To many of his colleagues, it reeked of theology, of Genesis retold in equations. The thought that the universe had a beginning stirred suspicion. In Cambridge, the great Arthur Eddington, who had championed Einstein's relativity, dismissed the notion outright. He admitted the idea was scientifically sound, but declared it repugnant to him, the suggestion that time itself had been lit like a fuse. Einstein, too, resisted. When Lemaître presented his solution, Einstein acknowledged the mathematics but rejected the conclusion. "Your calculations are correct," he said, "but your physics is abominable." To Einstein, the thought of a cosmic beginning was philosophically troubling, too reminiscent of creation. He had once tried to preserve a static universe with his cosmological constant, and now this quiet Belgian priest was undoing that dream entirely. Lemaître endured the skepticism with calm resolve. He was not trying to force scripture into science. He drew a careful line between his faith and his equations, insisting that the two spoke in different languages. His primeval atom was not divine revelation, it was what the mathematics demanded, and what the observations would one day confirm. In many ways, he stood alone. Neither fully embraced by theologians, who expected him to turn science into doctrine, nor by physicists, who feared his ideas leaned too close to religion, he occupied an isolated frontier. Yet in that solitude, Lemaître carried something remarkable, the first true scientific vision of cosmic origins. Imagine, for a moment, the boldness of his thought. To take the galaxies, stretching outward into the void, and reverse them in imagination. To gather them back, closer and closer, until all the stars, the planets, the atoms themselves, collapse into one, a single, primordial fire. Not a place within space, but the birth of space itself. Not a moment within time, but the ignition of time itself. Lemaître did not yet know of cosmic microwave background radiation, the afterglow of that beginning. He did not yet know of primordial nucleosynthesis, when hydrogen and helium were forged in the first minutes of expansion. But he glimpsed the essential truth, that the universe was not eternal and unchanging, but dynamic, evolving, and finite in age. The scientific world was not ready to follow him. For decades, his theory was marginalized, treated as a curiosity, often conflated with myth. It would take years of accumulating evidence, the discovery of the cosmic background in 1965, the detailed mapping of its ripples by satellites like COBE, WMAP, and Planck, for his lonely vision to be vindicated. Yet history remembers. In the silence of the 1920s, when the cosmos was still thought by many to be timeless, one man dared to speak of its birth. Georges Lemaître carried the first light of the Big Bang in the form of a question, and though the world doubted, the universe itself would one day answer. And so, beneath the skepticism and the dismissals, a quiet revolution had already begun. The universe had a story. And somewhere in its depths, written into the glow of every star, lay the memory of that primeval atom, the first seed of everything.
By the middle of the 20th century, the universe had become a battlefield of ideas. The telescope had revealed a cosmos in motion, galaxies retreating into the night. Yet the question of origin remained unsettled, and two rival visions stood locked in opposition, one finite, one eternal. On one side was the Big Bang, the daring child of Lemaître's primeval atom. It pictured the universe as a story with a first page, a fireball of unimaginable density from which all things emerged. It suggested a beginning, a cosmic birth, a universe with an age and a destiny. On the other side stood the steady-state theory, shaped most famously by Fred Hoyle, Hermann Bondi, and Thomas Gold. It was an audacious alternative. According to their mathematics, the universe could expand forever, yet never change in its essential character. As galaxies fled apart, new matter would be created, hydrogen atoms emerging continuously from the void, enough to fill the growing gaps. The universe, in this vision, had no beginning and no end. It was eternal, timeless, self-sustaining. The contrast was stark. The Big Bang implied a singular origin, a moment when time itself ignited. The steady state offered a universe immune to history, unburdened by creation. It was a debate not only of equations, but of philosophy. Fred Hoyle, with his sharp intellect and sharper tongue, gave the controversy its most enduring label. Speaking on a BBC radio broadcast in 1949, he dismissed Lemaître's idea as the Big Bang, a mocking phrase meant to underscore its apparent absurdity. Yet the name, meant as ridicule, stuck like a spark to dry wood. From then on, the theory carried the moniker that would define it. Behind the scientific arguments lay deeper currents. To many physicists, an eternal universe carried a certain comfort. It required no beginning and, by extension, no metaphysical cause. In the climate of the mid-20th century, with its suspicion of theological overtones, the steady state appeared philosophically safer. A universe that had always existed seemed less vulnerable to appropriation by religion. By contrast, the Big Bang raised unsettling implications. If the universe began, what or who began it? The Cold War backdrop only sharpened the stakes. Science was no longer an isolated pursuit of truth. It had become entangled with ideology, politics, and cultural identity. Western scientists debated cosmology under the shadow of atomic weapons and existential threat. In the Soviet Union, some philosophers and party officials distrusted the Big Bang precisely because it resembled a creation story. An eternal cosmos fit more comfortably with the materialist philosophy of dialectical Marxism. Thus, the debate over the universe's age became not just a question of observation, but of worldview. The steady-state theory held undeniable elegance. It preserved what cosmologists called the perfect cosmological principle that the universe looks the same not only in every place and in every direction, but in every moment of time. It painted existence as infinite and unchanging, a sea without shores, an ocean without dawn or dusk. For those uneasy with the idea of a cosmic beginning, it was irresistible. And yet, the Big Bang held a different kind of power, not of symmetry, but of history. It proposed that the universe carried within it the scars of its own birth. If matter and energy once blazed in a fireball, then some remnant of that heat should still linger in the fabric of space. The theory hinted at testable predictions, fingerprints waiting to be discovered. Through the 1940s and 1950s, the two models dueled in conferences, journals, and lecture halls. Observations of distant galaxies and radio sources began to weigh in, but the evidence was not yet decisive. Each side sharpened its arguments. The steady state required a mysterious process of matter creation, never observed in laboratories, but posited as a quiet necessity of expansion. The Big Bang, for its part, demanded faith in an event beyond ordinary physics, a singularity where known laws broke down. For a time, the battle seemed balanced. The steady state offered eternity, the Big Bang a fiery beginning. One model protected the comfort of permanence, the other embraced the vulnerability of change. To choose between them was to choose between two visions of reality itself, an endless cycle without origin, or a fleeting burst with a fragile history. As the debate raged, no one could know that the universe itself had already chosen a side. Hidden in the darkness, faint and omnipresent, the afterglow of creation still whispered across space. But in the middle of the 20th century, it remained unheard, a cosmic secret waiting to break the deadlock. Thus, the 1940s and 1950s became an era not only of rivalry in geopolitics, but of rivalry in cosmology. The Big Bang and the steady state, two ideas born of the same mathematics, wrestled for supremacy. One would fall, the other would rise, but in that struggle humanity glimpsed something deeper, that the question of beginnings is never merely scientific. It is also philosophical, even existential. In debating the universe, they were also debating themselves, their place in time, their longing for permanence, and their unease with creation. The cosmos had become a mirror, and in it, humanity saw both its doubt and its wonder reflected. The debate between eternity and origin lingered in the mid-20th century like a cosmic stalemate. The steady-state theory held its elegance, the Big Bang its daring promise. Yet both awaited a verdict that only the universe itself could deliver. That verdict would arrive not in the pages of philosophy, but as a whisper of light, the faintest echo of creation still adrift in the sky. The story began decades earlier, in the 1940s, when three theorists, Georges Lemaître, Ralph Alpher, and Robert Herman, followed the mathematics of a universe born hot and dense. If the cosmos once existed in a fireball of unimaginable temperature, then it could not have cooled into silence without leaving behind a trace. That trace, they reasoned, would not shine in visible light, but in microwaves, radiation stretched thin by expansion, suffusing the heavens in every direction. Their prediction was precise, a glow just a few degrees above absolute zero, filling all of space like an invisible ocean. But in an era without the instruments to detect it, their calculation drifted into obscurity. Their papers gathered dust in library shelves, their idea quietly dismissed or forgotten. For nearly 2 decades, the universe's most telling clue lay hidden in plain sight, awaiting rediscovery. Then came 1965. At the Bell Telephone Laboratories in New Jersey, 2 young radio astronomers, Arno Penzias and Robert Wilson, were testing a sensitive horn-shaped antenna designed for satellite communication. Their work was not driven by cosmology, but by engineering. Yet as they calibrated their instrument, they encountered an anomaly, a persistent hiss of radio noise that refused to vanish. They chased the interference with scientific rigor. Could it be the city of New York, glowing faintly on the horizon? No. Could it be equipment malfunction, a fault in the electronics? Tests said no. Even the nesting pigeons inside the antenna and the droppings they left behind were evicted and cleaned away, yet the noise remained steady, uniform, unyielding. What Penzias and Wilson heard was not earthly at all. It was celestial. A signal not from a single source, but from everywhere. No matter where they pointed the antenna, the hiss was the same. It came from the universe itself, from every patch of sky, constant and inescapable. At the same moment, only a short drive away at Princeton University, a group of physicists led by Robert Dicke had been preparing to search for precisely such a signal, the afterglow of the Big Bang predicted years earlier by Alpher and Herman. When news of Penzias and Wilson's discovery reached them, the pieces fell into place. The faint hiss was not interference. It was the cosmic microwave background, the fossil light of creation, stretched across time. The implications were seismic. For the first time, the universe revealed direct evidence of its fiery birth. The radiation was not a metaphor, not a theory, but a measurement. It bathed the cosmos in a uniform glow at 2.7 Kelvin, exactly as the Big Bang model had foretold. The steady-state theory, elegant as it was, could not account for this ancient firelight. It collapsed under the weight of observation. The universe had spoken with clarity. It was not eternal and unchanging. It was born in heat and expansion. For cosmology, this was a moment of irreversible transformation. Ideas that had balanced on the edge of philosophy gave way to a single narrative grounded in evidence. The Big Bang was no longer speculation. It was reality inscribed in the sky. Every star, every galaxy, every atom bore witness to an origin written in radiation. And yet, the discovery carried not only scientific weight, but philosophical resonance. To know that the universe glows with its own memory is to confront time itself. The light detected by Penzias and Wilson had traveled for nearly 14 billion years, crossing eras of cosmic history, expanding with space itself. It was a message from a moment when atoms first formed, when the cosmos cooled enough for light to break free and race unbound into the future. The faint hiss was more than noise. It was a cosmic relic, older than stars, older than galaxies, older than the very scaffolding of the heavens. It was the echo of creation, still humming through the void. The discovery of the cosmic microwave background marked the end of one dream and the confirmation of another. The steady state, with its eternal comfort, faded into history, remembered as a beautiful, impossible vision. The Big Bang rose triumphant, crowned not by philosophy but by observation. The universe had a beginning, and that beginning left its mark. In the silence of their antenna, Penzias and Wilson had stumbled upon one of the greatest discoveries of the 20th century. A faint hiss became the roar of truth, and in its sound, humanity heard the universe confess. It was born in fire. It was born in time. It was born.
The universe had spoken. Its ancient whisper, the cosmic microwave background, declared that space and time themselves had once been compressed into a furnace of impossible density and heat. With that single revelation, the most enduring human dream, that of an eternal, unchanging cosmos, dissolved into silence. For centuries, eternity had been the natural assumption. Philosophers from Aristotle to Spinoza had imagined existence without origin, a universe without birth or death. Even scientists in the early 20th century clung to that vision, drawn by its stability, its refusal to require a first cause. But the discovery of the afterglow of creation in 1965 shattered that equilibrium. It was no longer speculation, no longer philosophy. It was measurement. The universe was not eternal. It had a beginning. The shock rippled across the scientific world. To accept that time itself had a point of origin was to accept that there was once a before, in which no before existed, a concept that strained both language and reason. The very framework of physics was forced to confront its own boundary. What does it mean for space and time to have a birth? What does it mean for existence itself to flicker into being from a silence beyond silence? Not all were ready to embrace the revelation. Fred Hoyle, who had mocked the Big Bang with the very phrase that became its name, never fully conceded. To him, the notion of a universe springing from a singular beginning remained philosophically unsatisfying, perhaps even absurd. Others, too, resisted. The discomfort was not simply scientific, but existential. If the cosmos had a beginning, what lay beyond that boundary? And why did it begin at all? Theological echoes stirred beneath the debate. To speak of a beginning was to echo ancient creation stories, to whisper uncomfortably close to the language of Genesis, "Let there be light." For some, the Big Bang seemed to offer science's reluctant confirmation of religious intuition. For others, it was an intrusion, a dangerous overlap between physics and faith. The guardians of cosmology sought, often with deliberate care, to separate the scientific from the theological. The Big Bang was not creation in the religious sense, it was expansion, governed by equations, unfolding in time. And yet, the line blurred. The very act of tracing the universe back to its earliest fraction of a second carried implications beyond physics. Theories could describe what happened after the first instant, the rapid inflation of space, the cooling of plasma, the birth of matter, but not the instant itself. The singularity, that 0 point where known laws fail, remained beyond reach. Here science pressed against the edge of mystery, and beyond that edge, silence reigned. For philosophers, the shock was equally profound. The steady-state cosmos had offered comfort. A universe without beginning required no explanation for its existence. But a universe with a first moment posed the oldest of questions in sharper form: why is there something rather than nothing? If time begins, what does it mean to ask what came before? Such language collapses, for before has no meaning outside of time. In its place, humanity faced a conceptual abyss, a place where even imagination falters. The discovery reshaped cosmology's role in human thought. No longer could it be a science of static structures, of galaxies arranged in infinite time. It became instead a science of origins, of beginnings written into the very fabric of radiation. The cosmos was not a stage without curtain or clock, it was a story with a first page, its prologue imprinted on the sky. But the shock did not paralyze. Instead, it provoked an era of extraordinary creativity. Scientists began to ask, what mechanisms could explain the birth of the cosmos without invoking metaphysics? Theories of quantum fluctuations, vacuum energy, and cosmic inflation emerged, each seeking to describe how something could emerge from a state that seemed like nothing. These were attempts not merely to calculate, but to rescue science from the haunting pull of theology. Still, the shadow of the beginning lingered. Even as inflationary models stretched the timeline backward, even as quantum cosmology proposed that the universe might be self-contained without a boundary, the existential weight remained. A universe with a beginning was no longer a matter of debate. It was a matter of evidence. And evidence carried consequences far beyond mathematics. In the silence of their laboratory, Penzias and Wilson had not only uncovered a signal of radiation. They had forced humanity into confrontation with the most unsettling truth of all, that everything, stars, galaxies, atoms, life itself, had emerged from a single moment in time. A moment that science could describe but not fully explain. The shock of the beginning was not merely the end of one theory and the triumph of another. It was the return of an ancient question, sharpened by data, glowing in microwave light across the sky. What is the origin of origins? What is the source of time itself? In the aftermath of that revelation, cosmology found itself walking a narrow ridge, between science and philosophy, between mathematics and metaphysics. On one side, the equations of general relativity traced the unfolding of spacetime from its first fraction of a second. On the other, the silence of the singularity loomed, an unanswerable question that no telescope could yet pierce. The discovery of the cosmic microwave background did more than settle a scientific debate. It reminded humanity that knowledge and mystery are bound together. To know that the universe had a beginning is not to diminish its wonder, but to deepen it. The cosmos was no longer infinite in age, but it was infinite in questions. And so the shock of the beginning remained, not as a wound, but as a frontier. A reminder that even as science advances, there are edges beyond which the human mind must gaze with humility. The Big Bang had won the argument. But it also left humanity staring into the abyss of time, asking what it means to be creatures born inside a universe with a first heartbeat.
For centuries, the night sky appeared as a silent ocean of stars, eternal, unchanging, without hint of its beginnings. Even the discovery of the cosmic microwave background, that faint afterglow of the Big Bang, seemed at first like a simple confirmation of theory. A uniform bath of radiation, stretched across the universe in every direction. But beneath that uniformity, hidden in the soft static of the cosmos, lay a deeper story. A story of patterns and imperfections. A story that would show how the entire architecture of galaxies and clusters was already written into the earliest light. It began in 1992, with a satellite known as COBE, the Cosmic Background Explorer. Launched by NASA, it carried instruments sensitive enough to measure variations in the ancient radiation at levels of just 1 part in 100,000. For 6 years, COBE scanned the heavens, listening to the afterglow with ears of unfathomable delicacy. When its maps were revealed, they showed something extraordinary. The cosmic microwave background was not perfectly smooth. It bore the faintest of wrinkles, minute anisotropies, tiny fluctuations in temperature scattered across the sky. These were not flaws, but fingerprints. They were the imprints of density variations in the infant universe, primordial seeds from which galaxies would one day grow. At a press conference, cosmologist Georges Lemaître tried to convey the enormity of the discovery. He called it like looking at the face of God. The phrase was controversial, but it captured the awe. For the first time, humanity had seen not only the glow of creation, but the first outlines of cosmic structure, a blueprint of everything that would follow. Yet COBE was only the beginning. Its resolution was coarse, its pixels broad strokes across the heavens. To truly decipher the script of the cosmos, finer eyes were needed. In 2001, NASA launched WMP, the Wilkinson Microwave Anisotropy Probe. Orbiting beyond Earth's shadow, WMP mapped the sky with precision 100 times greater than COBE. Its all-sky images revealed a cosmos written in exquisite detail, hot and cold patches no larger than 1/10 of a degree across, variations etched into the radiation when the universe was just 380,000 years old. From these patterns, cosmologists could reconstruct the early universe with astonishing clarity. The ripples in temperature corresponded to variations in density, the scaffolding upon which gravity would later assemble stars, galaxies, and clusters. The data confirmed inflation's predictions. The fluctuations were nearly scale invariant, just as quantum ripples stretched by inflation would be. WMAP delivered not just pictures, but numbers, the fundamental parameters of the cosmos. It measured the universe's age with remarkable precision, 13.7 billion years. It revealed that only 4.6% of the cosmos was made of ordinary matter, while 24% was dark matter and nearly 72% was dark energy. It transformed cosmology into a precision science, where once it had been speculative. And then came Planck. Launched by the European Space Agency in 2009, the Planck satellite pushed the boundaries further still. With instruments cooled to near absolute zero, it measured the cosmic microwave background with resolution unmatched by any mission before or since. Its maps of the sky were so precise they reached the limits of what light itself could reveal. Planck refined the universe's age to 13.8 billion years. It measured the Hubble constant, the rate of cosmic expansion, with extraordinary accuracy, though in doing so, it deepened a mystery. Its value differed subtly from measurements of nearby galaxies, hinting at unknown physics or hidden complexities in the cosmic story. The anisotropies mapped by Planck were not random noise. They were the fossil record of sound waves that once rippled through the plasma of the early universe, acoustic oscillations frozen into the fabric of the cosmos. Each peak and trough in the data told of pressure and gravity, light and matter, locked in a cosmic dance before the first atoms had formed. Together, COBE, WMAP, and Planck revealed the most detailed portrait of the infant universe humanity has ever seen. What appeared to the human eye as faint blotches of red and blue were, in truth, the seeds of galaxies, clusters, and superclusters. Every spiral of starlight, every great wall of galaxies, every cosmic void was already inscribed in those primordial ripples. In these maps, the universe's history was written not in myth, but in mathematics. The peaks of the cosmic power spectrum became the verses of its song, a melody stretching back to the first instance of time. Inflation, dark matter, dark energy, all found their signatures in the sky. And yet, there is something profoundly humbling in these images. They show not only the origins of structure, but also the vastness of what lies beyond. The observable universe, the 13.8 billion year old bubble we can see, may be only a fraction of a greater whole. The maps are not of everything, but of everything we can know. Beyond them lies silence, horizons forever out of reach. Still, within that silence, the echo lingers. The cosmic microwave background remains the oldest light in existence, a messenger from a time when the universe was young, when matter and radiation were still entwined. It carries with it the memory of creation, faint, fragile, but indelible. Cobe opened the door, WMP illuminated the path, and Planck etched the details with breathtaking clarity. Together, they transformed cosmology from speculation to science, turning the heavens into a measurable, mappable place. But behind the precision lies the mystery. For each answer, new questions emerged. Why do certain anomalies appear in the maps, cold spots, alignments, whispers of asymmetry? Are they mere chance or hints of deeper physics? Do they suggest hidden structures beyond our horizon or echoes of universes beyond our own? The cosmic echo is mapped, but not fully understood. It is both revelation and riddle, both clarity and enigma. And so the story continues as humanity gazes into the ancient light, seeing not only where the cosmos came from, but how much remains unknown. For much of the 20th century, cosmology had converged toward a triumph. The universe had a beginning. It expanded from a fiery origin. Its primordial glow had been mapped in exquisite detail, and its structure traced back to quantum ripples in the dawn of time. By the mid-1990s, it seemed as though the great cosmic puzzle was nearly complete. The equations of Einstein, the discoveries of Hubble, the predictions of inflation, the confirmations from Cobe and WMP all appeared to converge on a single coherent story. And then came 1998. That year, two independent teams of astronomers were engaged in a quiet but ambitious project to measure the expansion rate of the universe by observing distant-type ice supernovae, exploding stars that shine with a consistent brightness, serving as cosmic beacons across the void. By comparing their observed brightness to their redshift, scientists could trace how fast the universe had been expanding at different epochs. The expectation was clear: the expansion should be slowing. Gravity, pulling on all matter, should gradually decelerate the cosmic stretch. But when the results were unveiled, they revealed the opposite. The supernovae appeared dimmer than they should have been, farther away than expected. The universe was not slowing down. It was accelerating. The announcement shook cosmology to its core. Overnight, the elegant narrative of a universe governed by known forces was disrupted by an unforeseen presence. Something was pushing the cosmos apart with greater and greater speed. A repulsive pressure woven into the very fabric of space. This force was named dark energy. It was not light nor matter, nor anything detectable by conventional means. It was invisible, inscrutable, yet overwhelming in its influence. Observations suggested that nearly 70% of the universe's energy was bound up in this dark component, driving the acceleration of cosmic expansion. Suddenly, what had been thought of as a settled story was revealed to be only a prelude. The greatest mystery of all lay hidden in plain sight, in the very emptiness between galaxies. The irony was profound. Einstein himself had once introduced a cosmological constant into his equations, a term representing a static energy of space, only to discard it later, calling it his greatest mistake. Yet in light of the new discovery, it seemed that the cosmological constant might have been prescient. Vacuum energy, the energy of empty space itself, became one candidate for dark energy. Quantum field theory predicts that the vacuum is not truly empty, but seething with fluctuations. Yet when calculated, the predicted energy density is staggeringly larger than what is observed, a mismatch of more than 120 orders of magnitude, the worst discrepancy in all of physics. Other theories emerged. Some proposed quintessence, a dynamic field permeating space, evolving over time. Unlike a cosmological constant, quintessence could change in strength, perhaps waxing or waning as the universe ages. Others suggested modifications to Einstein's general relativity itself, that gravity behaves differently on the largest scales than we understand in our laboratories or solar system. There were even whispers of extra dimensions, hidden influences from beyond the observable universe. But none provided clarity. Dark energy remained elusive, its essence beyond the grasp of measurement. Its implications, however, were undeniable. The future of the cosmos was rewritten. In a universe without dark energy, expansion would eventually slow, perhaps even reverse, leading to a collapse, the so-called Big Crunch. But with dark energy, acceleration means galaxies drift farther and farther apart. In billions of years, Distant galaxies will recede beyond the cosmic horizon, vanishing from view. The night sky will grow emptier, its tapestry of stars dissolving into isolation. The long-term fate of the universe is one not of collapse, but of solitude. Even more haunting is the possibility that dark energy itself may change. If it grows stronger, acceleration could become catastrophic, tearing apart galaxies, stars, planets, and eventually atoms themselves, a hypothetical Big Rip. If it diminishes, expansion could one day slow again, opening possibilities of cycles unknown. The uncertainty mirrors our ignorance. Humanity has measured its effect with precision, but its nature remains a riddle. Dark energy is more than a scientific puzzle. It is a philosophical tremor. It forces a reckoning with the limits of knowledge. How can the majority of the cosmos be made of something unseen, undetected, unnamed? For centuries, cosmology sought to strip away myth and reveal a rational order. Yet now, science itself encounters a mystery so vast that it evokes the same awe, the same humility, once stirred by ancient mythologies. The discovery did not end the story of the Big Bang. It transformed it. The universe is not merely expanding, it is accelerating into an unknown future. Cosmology is no longer the tale of a single beginning, but of a horizon that recedes faster than comprehension. Each observation brings sharper data, yet the central question remains unresolved. What is the force that drives the universe apart? In the end, dark energy is less a solution than an opening, a reminder that the cosmos still holds secrets beyond imagination. Just when the narrative of the universe seemed secure, the void itself whispered a deeper enigma. The expansion continues, but so too does the mystery. The story of creation, it seems, is still being written.
In the beginning, there is silence. Not the silence of an empty room, nor the silence of a starless night, but the silence of the unknowable, the silence at the edge of thought itself. Cosmology has traced the expansion of the universe back through time, past galaxies, past the glow of the cosmic microwave background, past the birth of atoms and light itself. Each step closer to the origin brings sharper clarity, until it does not. At the threshold of the Big Bang, physics reaches a wall. According to general relativity, the equations that describe the curvature of space and the flow of time, the universe began as a singularity, an infinitely dense point where the laws of physics cease to function. But infinities are not features of nature, they are signals of ignorance. A singularity is not a true description of reality, it is the breakdown of a theory pushed beyond its limits. The Big Bang, then, is not the ultimate beginning. It is the horizon of our understanding. To peer beyond this horizon, physicists seek a new language, a theory of quantum gravity, uniting the microscopic rules of quantum mechanics with the vast geometry of relativity. It is a frontier of speculation, but one rooted in rigorous pursuit. String theory imagines that the smallest ingredients of nature are not points, but vibrating strings, their harmonies weaving particles, forces, and perhaps even spacetime itself. In certain models, our universe could be a membrane, a brain, floating within a higher dimensional space. A collision between brains might ignite what we perceive as a Big Bang, one among countless cosmic births. Loop quantum cosmology takes another path, quantizing space itself. In this vision, the universe is built from discrete loops of spacetime, finite in size, woven together into a vast network. Near the supposed singularity, these loops prevent infinite collapse. Instead of a beginning from nothing, the universe bounces. A prior cosmos contracts, shrinks to a minimum, and rebounds into expansion. The Big Bang becomes not a birth, but a bridge. These ideas raise a profound question: did something exist before our universe? The mathematics allows for it. A pre-universe, with its own stars and galaxies, crushed in its final collapse, giving rise to ours. Perhaps our cosmos is but one cycle in an eternal rhythm of expansion and contraction, creation and destruction, written into the very structure of time. And yet, another possibility stretches even further. Inflation, the rapid expansion that smoothed the infant universe, may itself be eternal. In this picture, pockets of inflation never end, forever bubbling into new universes. Each bubble becomes a cosmos, with its own laws, constants, and structures. Our universe, vast as it seems, could be just one drop in an infinite sea, the multiverse. It is an idea both intoxicating and troubling. If countless universes exist, then our cosmos is not unique but one among an immeasurable ensemble. The fine-tuned balance of forces that allows stars and life might be explained not by design, but by vast numbers. In an infinity of worlds, some must allow life, and we find ourselves in one of them. But how does one prove what lies beyond the singularity? These theories live at the edge of science, where mathematics dares to step but experiments cannot yet follow. There are hints, patterns in the cosmic microwave background, subtle imprints of pre-Big Bang fluctuations, or signals in the distribution of galaxies, but nothing yet definitive. And so the singularity remains both a boundary and a beacon. It reminds humanity of its limits, yet also calls forward, whispering that the story is not complete. The Big Bang is not the first page of creation, but the fold in a book whose earlier chapters are missing. To go beyond the singularity is to confront the deepest mystery, not just how the universe evolves, but why there is something at all, rather than nothing. Perhaps the universe is eternal, without beginning or end, flowing through endless cycles. Perhaps it is one spark in a multiverse of infinite beginnings. Or perhaps the true origin lies in a physics yet unimagined. At the edge of knowledge, the cosmos offers no final answer, only horizons that retreat as we approach. The singularity, far from a conclusion, is an invitation. An opening into mysteries still unwritten. In the vast theater of the cosmos, the deepest mysteries do not reveal themselves easily. They lie hidden in faint echoes, in subtle ripples, in whispers written into the structure of reality itself. To approach them, humanity has built instruments that stretch both imagination and technology to their limits. Each tool is a kind of sense, an extension of the eye, the ear, and the mind, reaching further than human perception ever could. The James Webb Space Telescope, launched in 2021, now drifts in silent vigil a million miles from Earth. Its golden mirrors unfold like the petals of a celestial flower, tuned to capture the faintest light stretched across billions of years. Unlike Hubble, which saw galaxies in their youth, Webb peers deeper, into the faint embers of the first stars and galaxies. Its infrared eyes detect light so redshifted by cosmic expansion that it began its journey when the universe was only a few 100 million years old. Through Webb's gaze, astronomers now witness galactic structures assembling earlier than once imagined, challenging models of cosmic evolution. Some galaxies appear surprisingly mature, heavy with stars, as if cosmic history had hurried its script. Each observation forces a rewriting of the earliest chapters of creation. While Webb peers outward and backward in time, another machine listens inward, beneath the surface of reality itself. At CERN, the Large Hadron Collider hurls protons together at energies approaching those of the universe's first instance. Each collision is a controlled reenactment of conditions a fraction of a second after the Big Bang. Detectors surrounding the collisions capture sprays of particles, fleeting signatures of nature's hidden architecture. In 2012, this machine revealed the Higgs boson, the long-predicted particle that gives mass to matter. But deeper questions remain. Could new collisions uncover unknown fields, hidden dimensions, or exotic states of matter that shaped the birth of the cosmos? Each experiment is an attempt to glimpse the unseen scaffolding beneath reality's surface. Beyond particles and light, another messenger carries clues from the beginning: gravitational waves. These faint ripples in spacetime, first detected in 2015, are vibrations of the universe itself. Born from cataclysms like colliding black holes, they prove that Einstein's vision of spacetime as a living fabric was true. But beyond stellar collisions, scientists hope to detect a far older music: primordial gravitational waves. Such waves would be relics of the universe's first heartbeat, frozen vibrations from the earliest seconds after the Big Bang. Unlike light, which is blocked and scattered, these waves would travel unhindered, carrying with them the raw memory of creation. Detecting them would be like touching the tremors of the cosmos's birth cry. The search does not end here. On the horizon stand instruments of breathtaking ambition. The Cosmic Microwave Background Stage 4 project, CMB-S4, will map the ancient afterglow of the Big Bang with unparalleled sensitivity, searching for subtle imprints of inflation, the hypothesized moment of runaway expansion. In the 2030s, the Laser Interferometer Space Antenna, or LISA, will unfurl across millions of kilometers in orbit, listening to the cosmos with exquisite sensitivity to gravitational waves. It may capture signals from the mergers of supermassive black holes, or even echoes of events before the first stars. Together, these instruments will press closer to the veil of the first moment. Every telescope, every collider, every detector is part of a single human endeavor, to pierce the darkness of origins. Each device is not merely a machine of steel and circuitry, but a question made tangible. They ask whether the universe carries, in its oldest light and faintest vibrations, the record of its true beginning. And so the search continues. Humanity builds its instruments not only to measure, but to listen. To tune into frequencies that the cosmos has carried across eons. To search for whispers of the unspoken, for patterns older than galaxies, for signals that may tell whether time itself had a first dawn, or whether creation flows from something deeper, eternal, and unseen. The quest is not one of answers alone, but of reaching. Each discovery folds open new mysteries. For in every faint signal lies a paradox: the closer one approaches the beginning, the further that beginning seems to recede. The James Webb Space Telescope, CERN's collisions, the vibrations of spacetime, and the visions of future instruments, each is a lantern held against the dark. None yet reveal the final truth. But together, they form the constellation of human curiosity, shining against the silence of the unknown. The story of the cosmos is still unfolding. The tools we build are not the end of the journey, but the bridge toward questions still unasked. They remind us that the universe is not a solved equation, but a mystery that grows deeper the more it is explored. And at the edge of all knowledge, beyond the reach of mirrors, colliders, and detectors, lies a silence that invites humanity to dream again.
In the hush of the cosmos, a question lingers like an echo across eternity. What does it mean for time to have a beginning? The story of the universe often begins with a single phrase, the Big Bang. But even this monumental description is only a frame, a window cut into a vast and unfinished mystery. The equations of general relativity trace space-time back to a singularity, a vanishing point where distances collapse and time itself seems to dissolve. Yet in that moment, if it can be called a moment, the language of physics falters. The known laws that so elegantly govern galaxies and stars refuse to speak about the instant of origin. The haunting truth is that science has described the unfolding of the cosmos, but not its spark. It can map the expansion, the cooling, the formation of elements and galaxies. It can trace every structure back to quantum fluctuations in the infant universe. But when pressed to answer why there is a universe at all, or what ignited being from apparent nothingness, it remains silent. Can something truly arise from nothing? The question reaches beyond equations and observations. For in physics, nothing is rarely the void it seems. Quantum fields shimmer even in their lowest energy state. Virtual particles flicker in and out of existence. To some, the vacuum is not emptiness, but a restless sea of possibility. Could such a sea have given rise to all that exists? Or does the very concept of nothing collapse under scrutiny, revealing that what we imagine as absence is always, in truth, another form of presence? Philosophers have long wrestled with this paradox. From ancient cosmologies that envisioned eternal cycles, to modern reflections on creation ex nihilo, the tension has endured. Science, for all its triumphs, can describe the how of the Big Bang, but struggles with the why. The unfolding of space-time from an initial singularity may be mapped with precision, yet the reason there is a singularity at all remains veiled. Perhaps the difficulty lies in the limits of human language. To speak of before the Big Bang may already be a category mistake. If time itself began with the expansion, then before has no meaning. There was no waiting void, no dark silence anticipating creation, because anticipation itself requires time. In this view, the universe did not begin in time. It brought time into being. The very fabric on which before and after rest was woven at the moment of origin. Yet the human mind resists such finality. It strains against the boundaries of comprehension, asking, if not before, then what? If not from nothing, then how? This yearning is itself a kind of cosmic echo, a reflection of the universe becoming aware of its own obscurity. For in every question humanity asks about its origins, it is the universe speaking to itself, wondering at its own birth. Some scientists have turned to theories that stretch beyond the singularity. Quantum gravity, loop cosmology, and string theory propose that the Big Bang may not have been the first moment at all, but rather a transition, perhaps a bounce from a previous state of existence. Eternal inflation imagines a cosmos that births bubble universes endlessly, each one a flicker in a vast multiverse. In such visions, the Big Bang is not the beginning, but a beginning. Yet even here, mystery persists. If there is an eternal multiverse, what breathes existence into that infinity? What principle ensures there is something rather than an eternal void? The question remains unyielding. Science can describe the mechanisms of unfolding, but the spark eludes capture. It is as though one were handed a symphony sheet music, perfectly transcribed from its second measure onward, while the first note remains forever absent. The melody plays, the harmonies rise, but the origin is silence. And so the inquiry turns inward. What does it mean for beings of matter and thought to contemplate their own beginning? Humanity, formed of stardust and time, has become a vessel through which the universe reflects upon itself. The atoms of every brain were forged in the interiors of ancient stars, which themselves were born from the ashes of the Big Bang. Consciousness, then, is not an alien intruder in the cosmos, it is one of its emergent properties. To wonder about origins is the universe awakening to its own mystery. This realization carries both humility and awe. For if the spark of creation remains beyond grasp, then existence itself is not a solved riddle, but a continuing invitation. Every telescope launched, every collision studied, every ripple of space-time measured is an attempt to draw closer to that silence, to hear its contours, to touch its edge. Yet no matter how far instruments reach, there may always remain an irreducible mystery, the unlit horizon beyond all knowledge. And perhaps this is the deeper truth, that the cosmos is not a puzzle with a final answer, but a story that transcends endings. To ask why the Big Bang happened may be to miss the deeper wonder, that it happened at all, and that within its unfolding came beings capable of asking the question. Humanity is not outside this narrative, but within it, an expression of the very forces it seeks to understand. The tension between explanation and meaning, between the how and the why, may never dissolve. Physics will refine its models, uncover new laws, perhaps even trace the moment of creation with greater clarity. But whether it can explain why there is something rather than nothing remains uncertain. That question may belong not only to science, but to philosophy, to reflection, to the poetic silence where knowledge meets wonder. In the end, the Big Bang is not only a scientific theory, it is also a mirror. It reflects the limits of human understanding, the resilience of curiosity, and the astonishing fact that the universe, vast and ancient, has given rise to eyes that can look back, to minds that can imagine beginnings. The spark may remain hidden, but the search itself reveals something profound, that humanity is woven into the fabric of the cosmos, not merely as observers, but as participants in its unfolding. And so, the final reflection lingers. Perhaps the true meaning of origins is not to solve them, but to be transformed by the asking. To live within the mystery is itself to share in the wonder of creation. The universe does not simply exist, it becomes. And through humanity's questioning, it knows that it does.